Good morning, everybody. Welcome to the presentation portion of this year's symposium. My name is Nick Mundell. I'm the Director of Core Modeling at Thornton Tomasetti. For the first presentation today, I'm going to be talking about computational design, as many of our speakers are today. My goal is to give a little bit of a brief history on computational design, as well as give some context as to where Core Studio and Core Modeling work in relation to computational design. Essentially, what I'm going to try and do with this presentation is give an idea about where we've been with computational design, how do we get here, and where are we going to be going in the future. I'm going to use project examples and tool development to try and illustrate my point. At the end of the day, I'm going to be talking about things we make in the physical world and the tools we use to make these things, and how these things have changed over time and how computation has influenced it. So, to begin with, where have we been? Brief history of computational design. Back in 1885, state-of-the-art was skyscrapers in Chicago. In 1886, we have the development of the automotive industry with the fabrication lines of Ford Motors. 1903, the development of the aerospace industry with the Wright Flyer. And my goal here is just to point out that whilst these are three separate industries in historic terms, their eventual integration in the 20th century is what's really allowed computational tools to take off in the AEC industry. So, after 1800, where are we going to? In 1950, we have CAD, experimental research, essentially, in certain universities and fabrication firms, in this case, Citroën, the DS, and the development of the Bezier curve. 1970, we take CAD from being experimental and put it on commercial mainframes. In 1974, Charles Eastman's come up with a theory for glide, which is very similar to what we see in Revit these days. Dassault Systems is building planes in '68 using their own software. 1980, CAD gets adopted on personal computers. We have the release of AutoCAD in '82 and Rhino 3D in 1982 as well. Not sure everyone realized it. Rhino was that old. 1990, the adoption of BIM, Frank Gehry building complicated structures in CATIA in Barcelona. And then in the early 2000s, we have the release of version 1 of Revit, generative components in 2003. The key thing here I want to point out is mostly we're talking about the release of Grasshopper in 2007. Even in 2008, Herzog and de Meuron were building complicated structures in CATIA, which is not really an architectural platform. Not to say it's not good for the job, but it wasn't really democratized as a tool because it's very expensive. So, with that in mind, how did we get here? Specifically, Core Studio and Core Modeling. Thornton Tomasetti itself, the roots go back to 1949 with the launch of Paul Weidlinger Associates. In 2011, Robert Otani forms the Advanced Computational Modeling Group, essentially a lean, mean computational team whose goal is to spread knowledge through all of our offices. Through dual kind of focuses of parametric modeling and tool creation. In 2014, ACM Group is rebranded as Core Studio. Essentially, this is an expansion of the team at this point. The success on project work as well as the development of tools since 2011 led the firm to see the usefulness of computational team inside. And I will say that the modeling side of it and the tool development side is really closely intertwined in these years. Any projects that we work on are generally designed to facilitate tool development, or project problems that can be solved multiple times are best solved with tools. To describe the process that Core Studio goes through, I'm going to use some project examples, but at the same time, I want to talk about some of the tools that came out of those projects. As I said, one of the key features of Core Studio and Core Modeling is our close integration with each other. So the three projects I'm going to focus on and talk about how the project problems themselves led to tool development are 30 Hudson Yards, This was an early project in the kind of core studio days. Super tall tower in New York City, steel building, very complicated geometry, presented all sorts of problems. I'm also going to talk briefly about the shed, which I'm sure everyone here is familiar with in New York, Dulles Career Renfro, building at Hudson Yards. And then a somewhat random project, Vlad the Great. All three of these are going to be designed to illustrate how the projects and the tools are integrated together. So, 30 Hudson Yards. As I said, a super tall tower in New York, very complicated steel geometry. And essentially, the work that core modeling did on this project resulted in the development of 3 specific tool sets that are now being adopted pretty much across all of the projects that we work on. The first one on the bottom left there is framing repair. This is a response to the differences inherent in the geometries between models in Tekla, a steel detailing platform, and analysis models. There's always going to be discrepancies between the 2 geometries. Our goal is to treat them as one. So in this case, we developed a set of framing repair tools, which is essentially a graph library, nodes and edges, that allows us to apply algorithmic fixes across the whole building. So things like snap to node, snap to edge, designed to alleviate some of those geometric differences that might have been present between the 2 models. Falling out of the 30 Hudson Yards project was also the Octree search tools in our Grasshopper library. This is a set of components that allows us to compare 2 different geometries, and then once that comparison has been made, to transfer data between those 2 geometries. This is also one of the first projects where we were able to combine separate data streams into one BIM model. In this case, using the Octree components, we were able to map our SART model onto our Tekla model and transfer all of the force data, etc., onto that model. Same thing with our Excel documents, ETABS models, and RAM models that we use for the project, all feeding in to a Revit file, and at the end of the day, creating a set of drawings where all that information you see on the bottom right was automatically added. In the past, that would have been a manual process of people making markups, handing off the markups to a drafter, and somebody then manually inputting. Our goal with all of these projects is to be efficient and to try and find solutions that are applicable beyond the life of this project. As I said, both framing repair, Octree, and the model merging workflow you see on the bottom right there are now integral parts of pretty much any large steel project that we work on. The shed, obviously everyone's probably familiar with this geometry. We were involved at very early stages here, even early enough that DSNR let us play a little bit of design consultant here, suggesting some different aesthetic solutions for the structural framing. It was also the first time we got our 3D printer in Core Studio. Great to bring the physical world a little bit closer to the virtual, which I'll speak about a little later. This is another project where Core Studio was providing sort of multiple services to DSNR, including solar analysis. I'm sure you'll hear from Mustafa later, but he was in Core Studio at the time. It also resulted in our development of, or expansion of Design Explorer, which is now thread multivariable data visualization. Vlad the Great, an interesting project, proposal for a 30-meter tall statue to sit atop the largest tower in Russia, Federation Tower. Essentially, this was a project that required a very custom workflow. We had a complex mesh model provided by the artist, which was literally carved from clay. We had to develop a custom script to find the centroids of all the geometry to place structural steel objects. So this was a project where, without the interoperability tools we've developed in the past, specifically TTX, which is now Construe, delivery of this project would have been, well, at least modeling it would have been nigh on impossible in the platform that was required, which was Revit in this case. At the same time as we're being intelligent about how we place objects, we're also trying to use computational tools to make some difficult geometric tasks a little easier. On the bottom left there, we are measuring tributary area for wind analysis on the flames of the halo of the statue. A very difficult thing in 2 dimensions to figure out, but easy enough with the right tools in 3 dimensions. I said a very complicated geometry, many different options required. Again, a project where simply modeling it in the most appropriate platform, Revit, would not have been possible at the time, or at least far too cumbersome to be cost efficient. So all of these steel pieces were generated in Grasshopper computationally, and then using our proprietary tools translated directly into Revit. Where are we going? What I'm going to talk about here is a couple more project examples that refer to 3 key aspects I think are critical for computational design to continue to be an important part of the AEC industry. We're going to be talking about reality capture. I'm going to be talking about digital delivery. And I'm going to be talking about industry adoption. 3 critical things that I think these for us. When I talk about reality capture, project I'm going to talk about here is a photogrammetry project where we're trying to bring as possible into the digital. With digital delivery, predominantly Nature Cloud, this is a direct add to fabric project. We avoided creating any drawing whatsoever. I'm also going to talk about this big airport, which is a case of modeling being a very early project. A lot of benefits. So the tree. This was an artist's request who wanted to install a tree on her property in the shed. Thornton Tomasetti was asked whether we could essentially figure out if it was possible. So the size of the tree, the weight of the tree, would it fit in the door? And the most obvious way to figure that out was to leverage photogrammetry. So this was a a drone-based scan of the tree. Once the artist saw the results, she actually decided not to cut down the tree, which was the original intention, and asked whether we could 3D print an iteration from this. Obviously, there's a long way to go with photogrammetry in terms of reality capture. LiDAR is a little better, but still too expensive for most people. But we're really moving forward towards a place where the real world can be brought quickly and easily into our virtual environments and leveraged. What's a drawing? This project, Nature Clouds, installed in the Fields Museum in Chicago, is a hanging garden installation worked on with Branch Technologies. Essentially a series of steel substructures holding up a 3D printed substrate, which then holds up the plants inside of it. Like I said, this was a project where we avoided drawings entirely and went straight from the digital model into fabrication. We also are involved in developing the construction sequence and how things go together. All of this parametrically built, so any changes upstream result to direct changes to the model downstream. It's nice to have some projects that are actually finished to show some pictures of. Oftentimes in core modeling, we're working on stuff that isn't ready for showing just yet, but some lovely photographs here of it installed. Next project I want to talk about is the Pittsburgh Terminal. And this is an example of integration of a computational team at very early stages of a project. Essentially, the larger the scale of the project, I think the larger the possible benefits from integrating this sort of team into the project. So at the very beginning, we were talking about design iteration with the engineers. We were integrated into the design team to develop parametric models to essentially quickly describe the systems that the engineers were thinking about to the architects. Once we moved past that part into schematic design, because we were so ingrained with the team, it was easy for us to suggest some changes. So the architect's roof geometry was not completely fixed at this point, and we noticed that there was going to be a large number of unique columns beneath the roof surface to support it. Obviously, that results in a higher degree of fabrication costs, so we suggested possibly making some very slight changes to the roof pitch to try and limit the number of unique instances. Again, only possible because we were integrated at early stages. Wind trib comes up again as an interesting way to use computation. With a complex elevation, the Voronoi tools in Grasshopper are excellent at developing trib areas for analysis purposes. This is another model where we're talking about fabrication level detailing pretty much the whole time. All of the clash checking was integrated into the script so that any clashes that were found could be addressed before it was going to be sent to a Revit file. And at the end of this project, we even got into the construction side of it. So with a highly structured Grasshopper script behind the entire project, it was a very short step to try and create a construction sequence animation. Essentially with like I said, a highly structured model, you're able to group things easily, and then with a little bit of Grasshopper know-how, apply some transitions to those objects. So again, not just parametric modeling, but full service data visualization all the way through the project, wherever we can. And where do we need to go, or sorry, what do we need to do to get there moving forward? What kind of computational design tools are required to continue to influence and expand its adoption? The 4 points I'm kind of throwing out there for discussion would be, and I guess some of these have come up in the previous discussion over the weekend. Critical for the adoption of computation further is going to be shared data standards. I think we all realize that interoperability is a pain in the butt. We've kind of given ourselves this problem, unfortunately, in this industry, and it's certainly something that we're going to need to address if computation is going to be achieve its fullest potential in the future. IFC is a small step towards that, and Thornton Tomasetti did the development of Construe, and before that TTX as a proprietary approach to that problem. But again, we can solve the problem in-house. It's not going to help us transfer files or information to collaborators and people across different disciplines, which, as I've said, is going to be critical for us to continue moving forward. Also heard mentioned yesterday the need for AEC firms to combine forces. We're never going to be able to compete with Google or Autodesk, the amount of data they can collect. So it's critical, I think, for us to team up, essentially. With those shared data standards, we should also consider combining data sets so that each firm isn't dealing with just 10 projects. They really have a larger set to deal with. We should also aim to lower the bar of difficulty, encourage adoption of computational methods. Nobody really likes to see a messy Grasshopper script, anybody, essentially. Core Studio and Core Modeling have put work into trying to, I guess, put a nice veneer on some of those complicated scripts with Swarm. And that, again, is designed to increase adoption by not allowing people to say it's too hard, I don't want to touch that tool. I also think the use of simulation and logistical methods for pushing further out into the virtual, or pushing further out from the virtual into the physical world is going to be necessary. So obviously there's a lot of physical world environments that we need to address in our models. We're usually making assumptions about it. Access to sensor data is going to be critical moving forward, live information. All of these things are going to be important for computational tools to continue to be as critical as I think they are in our industry currently. Okay, that's the end of my presentation. Thank you very much, everybody. Appreciate you joining early this morning for the first presentation. Probably different time zones, quite tricky. And I'll open up the floor to questions if there are any.
Cool. You can go ahead and stop sharing your screen and then try your video again. And Charlie will come on as well, and he'll moderate Q&A.
Still no video, Shannon, sorry.
Thank you, Shannon. When I try to share my video, I get the message saying you cannot start your video because the host has stopped it.
Okay, no worries. Just go ahead.
You need
10 minutes
Charlie.
for Q&A.
Cool. Maybe Nick, you could just kind of put an
Yep.
image on the screen.
I'm gonna bring that sucker back up.
Cool. This is some pretty exciting work that gets to happen within the core modeling group. What was there? Can you kind of recall like what I call it a eureka moment, like one of these moments in time where you're working on a project and you're like, wait a minute, we could never have done this by working in 2D. Like we had to have done this parametrically in order to resolve this issue. Is there like one moment in time that kind of sticks out to you?
Yeah, I think I don't have any images of it here, but one of the first projects I worked on at Thornton Tomasetti was called the Abhat Airport. It was a kilometer-long building, steel, very odd shape, and very, very short timeline to deliver. There was essentially no way I could imagine that project could have been delivered without a parametric model. That was the obvious example that comes to mind. I think for me, I think the real eureka moment in terms of efficiency in a structural firm was the Hudson Yards project. This was again something that prior to the integration of ACM into the workflow, this would have all been done manually. So the drawing you see on the right there for a tower this size, you can imagine how many data points that is. So I think I was speaking with one of the CAD people who was working at Thornton Tomasetti at the time, and he said that it saved him about 1 month of work to have those streams combined, and that's huge. That's I don't know how many hours that is, but it's a huge amount of manual labor that we were able to remove simply through 3D visualization and 3D comparison. So 2 dimensions would not have got us here in this case.
It's kind of nice that you can get feedback from, a firsthand individual saying that this saved them, so much time, right? It then helps bring value to kind of what you're bringing to the project. Absolutely,
yeah. Hearing that kind of validated all the effort, because it was difficult. We were making things up as we went, essentially. The framing repair toolbox didn't exist before. We realized we needed it, and the core studio development team was able to provide it. Once it's there, like I said, that's pretty much used on any project that TT does these days that needs to translate between software. Mm-hmm. And we've put a lot of effort, I would say, from those days of it being all Grasshopper scripts. The tools you see on screen have now been given user interfaces, and like I said, trying to increase adoption by avoiding people having to open up messy Grasshopper scripts.
Mm-hmm. I think the value that comes from these applications is the fact that they've been tried and tested on projects, right? They've been validated, right? So
yeah, absolutely.
Validation moves forward.
Yeah, I think the real, in terms of other people who are thinking about integrating computation into their firm, I think the real key here is that you need both people who are working on projects and you need people who are focused on tool development. It's very difficult for that one person to have both roles, I think. So, in the early days of advanced computational modeling, it was, we had a really small team, and it was kind of everybody does everything. Once we kind of got more into a formalized situation, the app development team and the modeling team, still working together closely, but different focuses essentially. So the app development team can focus on project problems, and then because of their knowledge of process and programming, can suggest solutions to the team, and then go back to the development team and try and actually actualize those solutions. We're always looking for problems that can be replicated on different projects. That leads to the best tools. I will say a lot of the time core modeling is working on custom solutions, but we are always keeping our eye out for things that can be propagated across other projects.
Yeah, a moment ago, when you were talking about the Hudson Yards project, you alluded to one of the drawings there. And currently on almost all projects that are happening in all firms, 2D drawings are the kind of standard staple deliverable, especially for project milestones, 50% DD, 100% DD, so on and so forth, right? What would you like to see? How would you like to see projects submitted in the future? How would you like to see these deliverables change so that we don't have to go from these, really data-rich associative parametric models to the static 2D?
Yeah, I mean, I think, we're still all tied into drawings, right? I mean, at the end of the day, the guy on the site needs to look at a piece of paper to put the thing in the right place. I think from our side of it, where everybody I think on this call would be happy to avoid creation of drawings as part of their process. The digital models we make are getting better and better, more high fidelity. I think eventually the goal is going to be no paperless delivery and fully data-rich models handed off to the next person in the chain. However, that process is currently stymied by the lack of data standards. If you hand a file to somebody and they can't use it, then that's not handing them anything. So whilst I think digital delivery is going to be the goal in the long term, and we shouldn't be printing out drawings, what format that takes is still to be decided. And I think that's a critical question we need to answer.
Cool. We have a question from an audience member. Can you expand on the common problem of computational techniques being too difficult to adopt? If we simplify the tools too much, people simply use new tools without learning to think parametrically. Isn't the power of Grasshopper the ability for users to know their problems, to solve their problems?
Yeah, it's an excellent point. And I think something that we've been attempting to improve since the founding of ACM. We have a crack team of Grasshopper users who are really parametrically savvy, and like you said, using a software like that, you tend to root out the problems and you can see them where other people might not. I'm not sure I have a good answer for it. We've been trying it for a long time to increase adoption of Grasshopper and these tools across the firm, but unless it kind of impacts your everyday, it's not impossible to get an engineer or even a junior architect to pick these things up. Our approach has been a little bit of a veneer. Like I said, we're creating tools that will leverage Grasshopper scripts through Rhino inside, but not have people open up the actual program. And I agree that there's something missing there, and that you don't really pick up the mindset that we have in the group that I work in. I think long term it has to be about getting people as soon as they walk in the door. You're never going to convince a mid-level engineer or a mid-level architect to pick up these tools if it doesn't increase their efficiency. Well, it does increase their efficiency, but they don't see that. So I think you've got to get them young, essentially, and you've got to have people who are interested in these tools and want to improve. I also would suggest that a lot of these tools enable more complicated design. If you want to design a curvy thing, you're going to have real trouble doing it in Revit. So the tool you use is important.
Yeah, I agree with you. I think I don't think that of all the years that I've been doing buildings myself, I don't think I've worked on a single straight tower, and I wouldn't have been able to do any of it without some of these applications. But kind of piggybacking on the previous question, there's obviously varying different levels of talent within the industry. If someone wanted to start exploring some of these advanced modeling concepts, do you have any recommendations where they can start looking at and to start?
Yeah, I think the process I went through, I probably spent 6 months in Grasshopper scratching my head, and then there was a day where I figured out what the data structure meant, and it was all smooth sailing from there. I think it's about starting slow and getting the fundamentals. I'm sure every Grasshopper user out there has heard of the ModeLab Grasshopper Primer. Probably one of the best documents to start from. I think it's basically the Bible of Grasshopper. Adoption and long term, I think it's tricky. Like I said, you have to have the projects to work on, and I think we're lucky, Charlie. Like you said, I haven't worked on a straight tower in a while as well, and I think there is a little bit of a reinforcement loop there where we get all the complex geometries, and perhaps the rest of the firm isn't really exposed to it as much. It's a difficult problem to solve because obviously there's money involved with training people to do these things.
I think it's also worth shedding some light on kind of the time frame or the moments in time on a project when some of these modeling tools can be used. Obviously, they can be used from beginning to end to kind of carry a project through, but there's also moments in time where you can create kind of these singular solutions where you just kind of use it for a specific point in time for your project, right? Can you elaborate a little bit on that?
Yeah, I think the Vlad the Great project was an example where there was essentially there's never going to be a way to take this and replicate it on a different project. We're not going to get a 30-foot tall statue on top of a building anytime soon. So it is an instance where a really custom solution was required early on in a project. I don't think this necessarily has to be early in the project. The Hudson Yards custom solution was specifically for the construction document set, translating all that data across. So I think, there are opportunities at different points along a project. I think my pitch here for the Pittsburgh Airport, the go hard, go early approach is really important. I think if you can expose members of the team to your thinking parametrically, essentially they'll have ideas. Like in this case, we were involved very early in the project, and the concept to use Grasshopper to create the wind trib areas, that was a function of the engineer we were working with seeing Grasshopper in action. We showed him the Voronoi tools, and he was like, you know what, that could be really, really useful to generate my smart analysis areas. So it's really, integration of the team. It may not be that you can train everybody in parametrics, but as long as you're exposing them to the concepts and the process, that's just as beneficial, I think, in the long run.
Perfect. I just got noticed that was our last question. So I want to thank Nick and the folks in the core modeling for putting this presentation together and sharing it with us.
Yeah, thank you, everybody.